Back on their colleagues who are with them, whether they're likely to join. If not, we'll start. Okay. Last week we discussed about the joints and we looked at one of the components that enables the joint, that is the bearings that is between superstructure and substructure. Today we will look at other joints, something between superstructure and superstructure at the later half, and some of the special joints between superstructure and substructure. All right, so we'll go through that. So able to see my screen? Okay.
Yes, sir.
So today we will talk about STUs. STUs are nothing but in expansion, they are called shock transmission units. And other joints, when I mean by these joints, these are the deck joints between one deck and the others. Okay, so we look at them today. So what do you know about shock transmission units? Anybody knows anything about shock transmission unit? Nobody. You may not have used it, but at least you would have heard about it. It doesn't take impact. It doesn't take impact. Okay. That's why I want you to be one thing you should learn over a period of time. Nothing is hitting against each other. Impact as a force comes when two objects hit each other. The shock transmission unit is not like that. It essentially, the closest day-to-day example, if you want to know a shock transmission unit that you have probably seen or used it also, is your car safety belt. How many of you are familiar, or how does car safety belt work? The seat belt in cars. You don't need to apply brake. I would suggest next time you get into the car and engaging in the seat belt, you pull it fast and then pull it slowly. Do you notice a difference? Yeah. Your shock transmission unit is somewhat similar in nature, that when it is a connection between the superstructure and substructure, if the substructure has a fast acceleration, high acceleration, then the element between the superstructure and substructure will not allow that movement to take place. And if the displacement of the substructure is slow with respect to the superstructure, it will allow the displacement. Something akin to your car safety belt, but the working principles are slightly different, but just to get you the parallel between the two, that's what so shock transmissions units are those, and joints are the expansion joint, more traditionally between the bridges. We'll see that. Okay. Now, the shock transmission units are device used in bridges. They accommodate deformations and transmit force. Okay. So basically what you see is like you have seen motorcycles, cars, you have seen shock absorbers. All they do is that when you hit a bump, there is a sudden large deformation. What it does is it operates in the opposite fashion, that it doesn't transmit that much acceleration to you. It slows down the process. So shock absorber are the reverse of shock transmission unit. Shock absorbers reduce the impact of the shock on the human body riding a motorcycle or a car or a truck or a bus, whereas shock transmission unit actually transmits the shock from one object to the other. So please don't confuse the two, but they are in principle opposite of each other. Okay. So Shock transmission unit, what do? They redistribute shear between substructure. That's a primary aim. Okay. What do the joints do? They allow the relative displacements between two adjacent superstructure. They accommodate movements. Okay. That's the difference between shock transmission unit at the joints and the expansion joint. Okay. Now we look at shock transmission unit. Now, if you see this bridge, it's an example of in the transverse direction. In the transverse direction, what do you see? You see something, an upstand. You're all familiar with what these upstands are called in the Indian terminology or Indian codal context. What are they? Exactly. Seismic arrestor is also a type of shock transmission unit. What does it do? It prevents relative displacement between the deck and the substructure in the transverse direction. And if you devise a system of the same nature in the longitudinal direction, then it would also be a kind of a shock transmission unit. But I don't want you to use interchangeably the shock transmission unit and anti-dislodgement or displacement arresting devices. They are functionally different. They are functionally different, though end result might be a transmission of force. So be careful about interchangeably using. So this is a kind of short transmission device. It's a physical restrainer. Whenever there is a relative lateral displacement, this engages with the superstructure and prevents relative displacement. Okay. Now, based on the bridge breathing units and the bridge vibration unit, it is affected by the choice and the type and layout of the bearing. We have discussed some time back about the polar radiating and how the vibration can be controlled and how they are judged based on the kind of movement. And with the vibration unit, we decide which mass is in what do you call it, moving along with which substructure. That is how we do it. And in the based on bridge breathing unit, we allow where the relative displacement between one unit and second unit can take place. So these behaviors can be altered by the choice of the kind of joint system that we are talking about. Okay. Now, question that is normally, should the bridges have breathing units the same as vibration units? Should they have? And if so, why? This is a question that we quite often ask ourselves. And the main reason we do is we say that from practicalities of the joints that we can procure and fix in terms of the gap management between superstructure, we quite often have our breathing units and vibration units distinct from each other, or they kind of sometimes they interrelate and sometimes they are quite different. For example, for the bridge breathing unit in this example, if I had the same thing, you will come to an argument that the whole bridge is one unit, and in this case the vibration, similarly this vibration unit could also be one, but in certain direction, in certain other direction, they could be totally different. So therefore, the vibration units, you have to be very careful in how you look at it longitudinally and transversely. It's a matter of how much of the mass participates in the free vibration in each direction. That you have to be very careful about. Now, why is this aspect important? It has primarily, as you said, in the case of an earthquake design, we don't generally have a serious problem. And to understand how the and what causes earthquake, you have to understand that basically the Earth's crust, which is approximately what, maybe about uh, 40, 50, in some places 60 kilometers thick, out of the 3,600 meters kilometer radius. It's hardly, you can say, about 1%, 2% of the diameter, which is our crust. That is not one single mass of solid material. They consist of all these plates. So you have a plate, the whole crust is made of the plates, and These plates are constantly moving. These plates are constantly moving. So we are on what is called as a Indo-Australian plate, which is moving, which is actually moving in the direction of the Eurasian plate. So which directly affects us. And long time back means maybe about 50, 60, 70 million years back, our Indian landmass was separated from the Eurasian plate by a body of sea, which was called the Sea of Tethys or Tethys Sea. That's the name given. It doesn't exist anymore. And when this mass started to move, it was closer and attached to the African plate. When it started to move and move and hit, and then therefore due to that motion, Himalayas were created. All that is fine. And because of those movements, wherever these plates are moving, significantly at the joints of all these plates, you have an enormous amount of seismic activity. We'll understand a little bit of what seismic activity, what are the characteristics they possess, what do we need to know about them, how do they influence our design, what kind of inputs they gave to us. Okay, these are the things that you need to understand that. We have to understand that we are a part of, our country is a part of the Indo-Australian plate, which means we and Australia are kind of moving together. And you have this Pacific plate, which is the very large. This is the one. All around it, you have a large seismic activity going on. That is why this whole line is called the Ring of Fire. They are lined by either active or passive volcanoes in one part, and they have significant of seismic activity. That is why you will notice that Japan has got a large amount of seismic activity, and if you notice here, there's a Taiwan which has got a significant amount of activity here, very close to this plate. Then you have a California, which has a very large amount of active place. And if you notice, New Zealand compared to Australia, New Zealand has a very large amount of seismic activity. What it tells you, is that when it comes to earthquake engineering, also from building and bridges and infrastructure point of view, most of the solid research work in the field of earthquake engineering is done in Japan, in California, the universities in California, universities in Japan, and the universities in New Zealand. Okay, and surprisingly, you will also find fairly good earthquake engineering studies in Italy and Turkey, because they also have a fairly significant earthquake activities. And those of you who are familiar with the old British code, England does not consider earthquake as a loading at all in the whole country. They have no definition of seismic zone. You don't have to design any bridges in UK for earthquake. That's a nature's luck for them. So these are the places where movement of the ground takes place, because it's a constantly moving thing, and quite often the movements are going in a particular direction because the core of the earth is liquid and its earth is spinning in a particular direction, and all that leads to this particular direction of movement. It's not that they randomly move here and there. So these are the major tectonic plates, that is Indo-Australian, Pacific plate, Nazca plates, the South American plate, the North American plate, the African plate, and the Eurasian plate. Eurasian plate extends right from the Western Europe to all the end of Russia and including parts of Alaska. Okay. Now, there are also plates in the oceans. The oceans also have ridges and large depths of water that define the uh, movement place. So quite a lot of it. And when the earthquake happens, there are uh, certain situations that you have. There is a situation wherein the two plates are at rest. Okay, the two plates are at rest, and because they are not smooth joints, they are interlocked joints. So as the plate moves, there is a buildup of stresses or strain energy, whichever way you want to look at it. There's a buildup of this energy, and at the time of and the energy, and there is a certain capacity for these joints to resist that stress buildup. So there is no relative movement. But one day, as the what they call it, the amount of energy stored builds up so much that it will overcome the resistance between the plate, and then there is a relative movement. And at that time, what happens once you do the displacement, then basically what you're saying is the built up strain energy is released. And that released strain energy is what causes the various shock waves that travel through the crust, and that we call them as earthquake waves. We'll see some part of it now. We will not do great details about it because that I think is all a part of a full depth earthquake engineering course, but I'm just telling you basic idea what phenomena take place. And when this happens, once the necessary energy is released, they go back with the two plates displaced by whatever is the amount, and then they come back to the same neutral state, but not in the same original, but the relatively displaced way. This cycle keeps happening again and again. And based on the study of this, the tectonic studies, people are able to predict, okay, in this area there's a high probability of a large earthquake coming. There's a high probability because these plate movement have now been studied for a long time, possibly almost a century of studies there for almost all the plate. Sensors, strain monitoring devices have all been installed. They gather the data and then start predicting that, okay, in this place there's likely, but they still are not able to predict accurately that it will happen on such and such day or such and such time or in such and such place, because we don't have information to find out. Just remember that in this edge crustal boundary, we don't know which is the weakest point. And as you logically understand, like as a structural engineer, the failure always takes place in the weakest link, and we don't have enough data all along these crustal boundaries. For example, we don't have accurate data for all of them to say, okay, this is the weakest, or that is the weakest, or this is the weakest. We are unable to have that information. So we are not able to predict accurately where it is going to happen. But looking at the mass of the thing, the amount of movement that it plays, we are able to predict, yes, something is likely to happen next 5 years, next 10 years, next 15 years, of that nature. Okay. So that is how uh, this is the elastic rebound theory for the earthquake phenomena and the way the energy is released. Okay. So initially there is an elastic strain buildup, then there is a brittle rupture, and then there is a slip. These are the three stages in the form that we have. Now the question is, the movement here, what you have seen is the movement that is the relative slip. Now you can ask a question, when they are moving in a perpendicular direction, why does the slip take place? Because the meeting places are never normal to each other. Okay. So to all these things, you need something called a fault line. And then the sudden release leads to a concept of slip. The slip is an indirect measure of how much energy that has been possibly released. And there are methodologies that are being predicted now to, based on the measurement of slip, to actually find out what should be the definition of earthquake instead of the old scale of, we are normally doing by the uh, Mercalli scale and two other scales that you're familiar with, the Richter scale. All that, they are only qualitative. These will be able to do a quantitative prediction of what will be the magnitude of the earthquake. Right. So what you can see here is in California. What you can see that this grow was all in one line. And a post earthquake, you can see that there has been a lateral shift. It is not that they planted these trees in this fashion. This has happened. That means this is the line along which the rupture or the slip has taken place. And after the slip, this row of plants have all displaced. Some very interesting photographs to tell you physically this phenomena is real. What you and I are seeing is, say, at this place significant energy is released. The impact local to this area will be very large, but sitting at far away, we will only feel the vibration. Okay. So this is the line along which the slip has taken place. So there is a thing called the horizontal slip, and along that with that there is also, that means they only slide horizontally to each other. And then there is also vertical slip. What happens is that when the slip happens, one can go higher than the other. That's kind of slip also, depending upon the inclination of the interface between the two plates. So this possibility also exists, especially as you can see here, if the joint plate is an inclined one like that, that one of them is going to go up and the other one will remain at the down level. Okay. So there are two types of earthquake motions that are important for us to know. There is a near fault earthquake and there's a far fault. These terminologies you have known. Near fault earthquakes are all, you know, lead because of the slip, and it is near the so-called slip point. We use the word epicenter. That you can say indirectly, epicenter could be in the ground depth at the certain uh, meters or kilometers below ground, but at the close to the location where the grounds relatively slip, that is where you will see the significant impact of the ground motions near fault. Okay, they lead to the peak ground in this near the slip only near fault location. You will have large residual displacement. What it means is after the earthquake event, you will see the kind of displacement here. You will see this displacement. It is permanent. It will not go back. That is why it is used. The word is peak ground residual displacement. There will always be a permanent displacement between the two parts of the fault line. Okay. Then there is also a possibility that simultaneously there will be vertical. So there is in the case of near fault earthquake ground motion, there is also a slip in the vertical direction. That is what was illustrated in this, that there is a inclined fault line, not a vertical fault line. So when the strain energy builds up, logic tells you that this mass will go up and that mass will either remain same. That's what is likely to happen. If it is vertical one, then you will see a rise in this. This is the kind of a situation which we see in the case of Himalayas as an overall sense. But locally, there will also be a possibility of an inclined vertical slip of this nature. Okay. So, how do we as engineers distinguish the near the ground motions from far field and near field? Okay. So basically, in far field earthquakes, that is what we normally design. Please remember that unless you have a very active fault close to the bridge structure that you're designing, you will have very little of near field design effects to be considered. Okay. So in far field, you only say the disturbance reflected in the ground motion. So basically the energy released and the energy is transmitted as S waves and P waves. We'll talk about it a little later. Those waves will move the ground forward and motor like almost like you can say any sound waves through air, where you can see the solid particles move in an oscillatory fashion. Similarly, the ground particles and the ground mass moves in an oscillatory pattern like that. But in near field, what happens is the fault movements gets reflected in ground motion. So if you are near the fault line, then what will happen is you will see very large relative displacement possibility. For example, what I meant to say is, imagine that you had a bridge which was the slip has taken place this way. Imagine that you had a bridge that is crossing this fault line, say along this itself. Then what would have happened is, no matter what you would have done, this relative displacement, you would never have been able to sustain it, because that ground motion will completely be transmitted to the earth and there will be permanent residual displacement between, say, one foundation here and one foundation here. That effect is what is significantly to be considered when you are designing bridges with a near field effect. That is, there will be a large permanent displacement. Okay. Large permanent displacement will be there, whereas here there will be only an oscillatory displacement. You can see that this is what will be the significant difference between designing for ground motions near far field with far field effects and the near field effect. Okay. Now, with far field versus near field motions, we'll see the comparative action, what happens. So there are two parts. There is a fault parallel movement. That means the way this actually is modeled is, when the energy builds up happens, this kind of slips and comes back like that. That means there is a transverse movement along with the movement along the fault line. This is the fault line. There is a movement this way, and then there's a movement that way, and there's a permanent slip. That is a fault parallel movement. That means there's a movement parallel to the fault, and there's also a movement perpendicular to the fault. Okay, so there's a fault normal movement is also there. Both of them simultaneously happen in the what they call it happen. Now the question is, in the near field movement, the significant effect that you need to consider is the fault parallel movement. That's a very significant effect you need to consider in the near field motions. But when you are in a far field motion, you need to worry significantly about the fault normal movement. Okay, this fault normal movement, that is the movement perpendicular to fault. Both of them takes place. Okay, so don't think that only one will happen, but depending upon the location of the bridge, if your bridge is near to a fault, then you may have a significant fault parallel movement to account for in your design. And if your bridge is far from the fault line, then you will have to, the far field will have significantly fault normal movement. So it will just go up, come back. Yeah. Yes, somebody asked for fault normal. Yeah. Yeah. Sorry, I'm sorry. I'll correct it. You're right. Fault normal movement. So it goes and comes back. So each one of them generates two different kinds of waves in the ground, right? And these are some peak ground acceleration velocities for the near field and far field that have been measured. There's a vertical and horizontal acceleration that you can see. The dotted lines are the vertical one, and the bold line is the different version. And you can see that the peak ground acceleration for some of them, horizontal one, have been around what, about 1.8 times acceleration due to gravity, and the vertical ones have been centimeters per second. It's in measured in terms of the velocity. They're also quite high, 120 centimeters, about 1.2 meters, climbing up in the vertical direction. So these are all the measurements, which essentially, what does it tell you? It tells you that the energy waves will be in all directions. You will have in the direction of the fault, perpendicular to direction of fault, and in a vertical direction, which is going away from the what do you call it, the horizontal surface of the earth. That is why, as we understood initially, we used to design only for, we understood as a ground shaking. So we used to design for only lateral loads. Then we understood the concept of energy distribution, and then we started to design for something called structural response method. Lately, we have recognized that actually the waves will come in all the three directions simultaneously. So we have multi-directional earthquake design we have formulated, and that is what we follow now as a norm in almost all countries. But rest assured, none of these design methods that you're using will work for designing bridges near field ground motions. In near field ground motions, forces are not important, displacements are important. That's a part of another topic when sometimes when we have time later after we finish this program to understand a little bit about how the seismic engineering is developing. We will talk about what are the different ways of analyzing, what are different methods of designing structures, where are we today in terms of the whole world, what do we adopt, what the rest of the world does, and which direction we are progressing. That's a different topic. Here, if you recall, my course title is Introduction to Bridge Engineering. I'm not going to make you an expert in all this. I'm giving you an exposure to what all phenomena that happens and why our codes are design processes structured in a particular fashion. How did it get developed? That's my whole idea, just to introduce you to those aspects. Okay, so in the near fault ground motion, you have to worry about three aspects: the acceleration, the velocity, and the displacement. Okay. So in the case of near fault earthquake, the acceleration starts, peaks, goes in the other direction, comes back, and then dies down. This is just for one cycle is what. And in terms of velocity of the ground motion, it goes to a peak and comes down to zero. And when it comes to fault parallel displacement, it displaces and there's a permanent residual displacement left in the near fault. Now, when you talk about what we call it fault normal movement, they have a peak, they have a bidirectional peak. That means this is if within one cycle of this, it will end up going in this direction, and the velocities will not be that high, but it will also have a reversible one in each cycle. And as far as displacement is concerned, in the fault normal displacement will be net displacement will be close to zero. There will be only in fault parallel, there will be net residual displacement. There will be no net at the fault. We are not talking about it is near fault. That's why we are understanding the phenomena at near fault. We are not talking about what happens far fault. Okay. Far fault, you will not have any residual displacement. You will always have back to zero displacement for far field. Okay. Now, what you notice in the accelerogram measurements of near far field and far field observations recording of a what difference do you see is that at the time of what we call it earthquake, it's a pre-earthquake peak and then it is a dying down portion. You will notice that the everything slows down. The rate of change of acceleration with time also, that means the time taken is more from going from peak to down. Okay, this is what happens near fault. And when you look at displacement, you have a large displacement at the time it starts, and the displacements further subsequent displacements are there, leaving some residual displacement. Now, if you take a look at the far field, far fault ground motion or far field ground motion, you will notice that the net displacement is virtually not there unless there are some local faults. So it remains close to zero. And as far as the acceleration is concerned, at the time of this earthquake, you have multiple cycles that are going through and then damping, and it'll die down. Eventually, all the energy will dissipate and come down to equilibrium. So acceleration, the velocity and displacement, these are all, of course, they are all related terms. The rate of change of displacement will give you velocity, rate of change of velocity will give you acceleration. So with time, of course. So these are the kind of differences you will notice in the acceleration, ground acceleration. Please remember, these are not response spectrum. Okay. Now, when you have this is an example of fault normal motion. These are like fault parallel motion. There you will see the displacement will go perpendicular to the zero displacement, and finally it will come down to zero, and you have a peak oscillation. They are pattern wise, they are different. The two waves along the fault and perpendicular to the fault are different. Now, when you have such large release of energies, and there is a large possibilities of, since all the superstructure have inertia, we need to have a concept which helps us utilize the residual strength of the pier. So this is an example of a shock transmission unit. What does it do? It connects the superstructure to the substructure through a mechanism. This is the shock transmission unit. It looks like your conventional shock absorber. We'll see the details a little bit later. And what does it do when the ground, say for example, there are two possibilities of relative movement. One is a slow phenomena like creep, shrinkage, and temperature. Once they are slow, it will allow for the movement. So that means this will be, each one will be an individual breathing unit. Okay, but then you can have a ground acceleration wherein you will have a significant change in the what we call it, a relative displacement at a much faster rate. At that time, what will happen? It will not permit the relative displacement between them. and then it will become a single breathing unit. That means there will be no relative displacement between superstructure and substructure when the ground movement is so fast. Okay. So how does the shock transmission unit actually work? It has, as you can see here, it has two units, one connected to the superstructure, one connected to the substructure. So inside that, it is like a piston is there. Piston has orifice here, and there is a viscous fluid here. It is two chambers. When the what they call it, the relative displacements are slow, then the viscous fluid escapes from one chamber to the other chamber, allowing the movement to take place. But if the displacement is fast, this orifice is not big enough to permit that quick transfer of fluid, then it looks as if it will be locking up. So that is what is understood as how does the load displacement graph for this look like. In service load means, what it means is, if the rate of displacement, whatever be there, it will transmit a very small fraction of the force, and for slow movement, low velocity, it will keep that force will never get exceeded. It's a small value. But if there is a high velocity, that means the rate of change of displacement is high, then what happens is the displacement gets controlled and the force increases. So in the earthquake load, this is what happens. It has a high velocity relative displacement, and in service load, there will be low velocity. Why? The low velocity, creep, shrinkage, temperature are all slow phenomena. Whereas earthquake is a very fast phenomenon. The acceleration and the change of displacement with time will be very high. Okay, so this is how the load displacement phenomena changes between due to the shock. What does it mean? It means that when the slow movements are taking place, there's only an upper limit of this force that will come. So, like for example, we look at it and we say that in the case of potent PTFE bearing, we still consider friction. I'm not saying this is equivalent to friction, but conceptually it is as if it has an upper limit depending upon the design of your shock transmission unit. There will be only a very minimal force. Remember, any movement that takes place, there will be resistance. There is no such thing as a free movement. In the case of potent PTFE, that resistance, we call it as a friction. In this case, that will be the what we call it, the resistance within this fluid block. Okay. But when it comes to high velocity, there will be no relative movement. It will stop. The force will keep on increasing. The displacement will stop there. Then what happens is the superstructure and substructure will displace together. So why do we use it? We'll see the applications of it a little later. So we'll have to design for service case for the low velocity for a design threshold frequency. And in the case of high velocity displacement, we'll have to design the displacement, decide on the displacement. It will still displace a little bit before the STU engages, and thereafter the force becomes a full. So you have to take care of it both. So there are different types of shock transmission unit available. The behavior will be low velocity, there will be no limit on displacement, but there will be a limit on force. In the medium velocity shock transmission, displacement and force will go linearly. And in case of genuine shock transmission unit, the displacement will be limited and the force will keep increasing. Okay. Now, the question comes, now we come to the movement on the bridge deck. So we have a what they call it type of bearings, and we think we have seen free, guided, and restrained. What it leads to is the relative displacements between superstructure and substructure. Where do you use shock transmission unit? Suppose you have a restrained pier. So if the structure is continuous for say few spans, then the inertial forces due to seismic effects in the longitudinal direction will all go to that restrained bearing. So what does that mean? That means that pier and the substructure and that restrained bearing will be designed for a very large force in the case of an earthquake. But if we have attached the shock transmission units on multiple, for normal operation, there will be only small forces and everything. Anyway, the braking and traction is not significant. But in an earthquake unit, the inertial forces will be shared between the substructs because the relative displacement will be limited to that single small value as you've seen in the load displacement behavior. So where do you use the shock transmission units? Imagine that you have a three-span continuous structure, you have a restraint bearing, and you have the longitudinally guided bearing in all these things. So what happens is, in the case if you want to, if you don't do any other arrangement, then the bridge vibration unit in the longitudinal direction will consist of this mass of the full superstructure and this one pier only. But if you attach the uh, shock transmission units at all these locations, what it means is, in the case of a seismic event, this superstructure is also connected to this, is also connected to this. Then in the longitudinal sense, for that the full vibration unit becomes this all of it together. So you have changed the bridge vibration unit from this to this by introducing these shock transmission units at all the piers. Why do you do that? The question is, why do you do that? Obviously, you're making the structure stiffer by making multiple foundations attached, which means what? You're going to increase the total seismic force you attack. But what you're saying is basically, though my total seismic force is increasing, I'm going to use the residual strength in each one of them to share the load, thereby giving me a more economical design. At the same time, on the other hand, let us say instead of shock transmission unit, we had put restraint bearing, that also will give you the same thing as far as the bridge vibration unit is concerned. But then the problem would be there will be no breathability in the structure. So in the service load, you will end up getting an enormous amount of horizontal forces in the deck as well as in substructure, due to the fact that between creep, shrinkage, and temperature, the bridge is not allowed to breathe if you make all of them restrained. Okay, so that is how you balance out the requirement of breathability and balance out the requirement of the vibratability. Okay, so uh, in this case, uh, basically all these bearings that are shown here, they are the ones which are elastomeric bearings only. So if in the absence of the seismic unit, it will be as if it's a floating span. And in the case of seismic unit, these shock transmission units will come. So uh, the question to you is this good, bad, or would you like to suggest any changes? That I think you just uh, later on note it down and send me back in the form of a chat. Okay, comment on this concept whether it is fair or not. Now comes the question here. Uh, can you tell me, is there anything right or wrong? This is the superstructure, this is the pier cap, and you have a shock transmission unit connecting the superstructure to this. Okay, there's a small gap here. Okay, so is that good or that's bad? So suppose I had grouted it, then would it have become okay? There would be no other problem than that. Let us say, for argument's sake, I agree with you that assembling this with these small timber wedges and the gap is not a good idea. Absolutely not a good idea. But let us say, for argument's sake, same arrangement, but this gap was fully grouted. Would it become okay? Or would you still consider deficiencies in the system? If you consider deficiency, I want you to tell me what kind of deficiency. Common sense only, it's not a highly technical one. It'll be okay. Yes, please. What happened? What do you think? It will be all right, or it will still be not all right, even if I grout the gap? Don't be afraid of being wrong, because unless you attempt to answer, you will not catch on.
No, sir, it is not okay.
What is not okay? Please remember that if you answer one way, there will be a reverse additional question following. Don't be scared of that.
Yes,
But so what is not okay?
that compression unit, it is not having that proper. It's having some fault in that compression,
What do you mean by that?
that area.
What do you mean by the fault? Be more specific. What is the fault?
Sir, that I'm not know the technical term for what that black area that is not
You
aligned
mean
properly.
are you talking about that small portion of spring that is visible?
Yes, sir. It is not
No, that spring is part of the design of the shock transmission unit. That is not an issue at all.
okay.
That is not an issue at all. That is the
Okay,
kind of a spring that is just to make some small adjustment. That's all. But that's not a problem. So other than that, you think everything is okay? Yeah. Nobody else wants to try. Nobody else wants to try. Okay. I will go back and between this and this, do you notice any difference? So the angle is good or the angle is bad? The angle is good or the angle is bad? Why? Why is the angle not good? So so so
it not
if
give uniform compression throughout the system, and
what compression? So I
it is not.
okay, go ahead, go ahead. Sorry, you go ahead, tell me.
No, sir, it is not properly horizontal. If the system
If
moves
it is not
horizontally,
horizontal, what will happen? So are you telling me that all your members in any bridge will be always horizontal or vertical? It's a simple static issue, nothing complicated. You're in the right direction, but you're not able to connect why the inclination is not good. Okay, let's look at it from logically. Let's say the superstructure is uh, having a sudden displacement in this direction towards the left. Then this shock transmission unit will engage, right? And when it engages, it produces a axial compressive force in the transmission unit. You agree with that so far?
Yes.
That transmission, that axial compression will create a shear in the top. You have no choice in that matter because the relative displacement is horizontal, so these bolts will be in shear. But because of that inclination, it will also create a shear at the interface between the pier cap and the unit. Whereas in this instance, due to the, since it's a horizontal one, there will be only normal forces in the pier cap. This shear you cannot avoid because that's a generative cost. You cannot eliminate the shear because we are trying to arrest the relative displacement between this and this. So obviously anything you do, you have to apply a force opposing the direction of motion. So shear will always come there. Okay. But here it's a normal force. So the question is, you don't want the normal force is easier to design in the pier cap. Superstructure has a very large depth. So it is a much stronger member, can resist the shear and axial direction, but this will be a problematic one. So normally when you do the shear STUs, make sure that they are installed horizontally. Okay. Another good example of it, you can see in this case there are two. This is truly horizontal, correct? This unit is horizontal, and there's a pin joint here, making sure that you only have this shear you cannot eliminate. All right. What are the advantages of it? They're easy to fit. They also are good if you have, say for example, you had a bridge which you designed in, say let us say you designed it in 2000, and you had a certain seismic design codes and standards and using peak ground acceleration, and in 2000, say 23, 24, 20 years later, Government of India, or rather the code committee, has decided that we need to redraw the seismic map of India, and your bridge now has, say, maybe about 20-30% higher peak ground acceleration. Then what do? You cannot demolish the whole bridge. At that time, you can retrofit option. You go back and recheck your structural design and say if you have residual strengths in other pier, then you can say, okay, I will put up my shock transmission unit, thereby increasing the sharing of the load. Obviously, you're making the structures differ, but it may still have possibility to keep the bridge serviceable for longer duration in spite of the increase in the seismic demand due to rezonation of your country's earthquake risks. But it has a disadvantage. All such mechanical devices have a disadvantage that you need to maintain them. See, remember, as I showed you the picture in the operation, here I have seen, I showed you that there is a viscous fluid inside. This fluid needs to be periodically inspected and verified that it is there. You can't leave, and since it's all a man-made creation, obviously there's a chances that it will leak, it will dry, it will change its viscosity, it can have so many things possible. Okay, so therefore it requires to periodically removed, inspected, maintenance, and reinstalled. That's a disadvantage of this. But then we if you look at it as retrofit option, possibly that's no choice about it. That's a cost we have to pay because the demand side is increasing due to the change in the national regulation. Okay, that's what we will stop about the shock transmission unit. We move on to the joints between the deck. So these are joints, a functional element between the structural part, usually superstructure. I am not talking about that joint we have talked in terms of bearing and shock transmission unit, but we are talking now about the relative displacement in the horizontal direction of the deck. Okay, they accommodate also the boundary conditions considered in structural. That's what we saw the definition. This is what we saw the definition. We looked at the joints, and they are at relative movement due to all the force loads as well as displacement. That is the function of the joints to accommodate. All of them cause. The joints have relative moments in the longitudinal, transverse, and vertical direction. These are the possibilities. You also have rotational, transverse axis, longitudinal, vertical axis, possibly not much. And then you have rotation plus translation, possible depending upon the articulation, bearing, geometry, etc. So to determine the magnitude of moment we saw last time, we can get the magnitude of moment, both rotation as well as displacement from analysis. And when we have the translation points, we need to decide what kind of arrangement we need to make at these locations. Okay, so this is where we come back to recap about our bridge breathing units, because other than those forces, if you notice that in our loading, this temperature, shrinkage, elastic shortening, all of them are volumetric change related values. So they will depend upon how your structure is breathing, and therefore depending upon that, the amount and magnitude of the movement that you have to decide, and therefore also decide on the layout of your bearings. And we looked back, recap, and said that we should avoid skew spans because the direction of movement due to various phenomena are relatively completely changed, especially due to the inertial effects. Not only the thermal effects also have a difference because of the orientation of the fixed bearings, etc. So the joints that are there between the adjacent thing, there are different types of joint. The picture that you see here, this is called as a finger type joint. Finger type joints mean there is a finger on one superstructure, there is a finger on the other structure, they are all bolted to the deck, and this is meant for very large movements. And another variation of the finger type is what you see here. This is meant for movements generally in excess of 250 millimeters. Okay, so what is the role of these joints? They provide continuity of road surface between the superstructure and the abutment adjacent sand, and they accommodate movement, and they also withstand load. So I will not discuss about the quality and the nature of them, but to understand, this is a simple plate type joint which is just straddling for small movement. This is one of the earliest joints that we did. Then how do you do this? To design these joints, first you identify the sources of all the different possibilities. So estimate them from structural analysis, the movement to be accommodated, vertical, horizontal, all of them that you need to do. And expansion joints should be compatible for each bridge span. That means you should be able to decide on these movements and then decide on the nature and the type of the joints. Okay, it is not that one solution fits all is what you have to adopt. Okay, and these are provided at the most vulnerable location in the deck because they are at the surface. They also are subject to impact, vibration, wear and tear. All these things happen to these joints, so they require reasonably good maintenance. This gap should be of uniform width because if you don't have this uniform width, then your vehicle noise will be different when the vehicle is moving in different stretches of the deck. Okay, and there must be, even in the maximum temperature when the joint is closing, there should be a minimum 6 millimeter gap so that the waterproofing arrangement that you have doesn't get squeezed and crushed. Okay, so the ways to do this, fixing this expansion joint, there are anchored joints. You can anchor it with epoxy mortar, anchor bars, holding down bolt. There are vast variety of solutions for it, each one peculiar to this. Some of them don't have any anchor, but we'll see that example also. Okay. Now, what are the causes for joint movement? Straight thermal movement. These are don't go too much by the magnitude. 1 millimeter per movement per meter for in temperature gap of 50 degree. That's what is a rough estimation is. Then racking movements in skew joints, because in skew joints the deck oscillates like that because of the nature of the direction of the deck, the magnitude complexity varying with the angular skew. You have vibratory movement from heavy traffic load, which is both vertical and it can be horizontal because of the vibration of the substructure. And then you have a strap and rotation due to heavy load. That means the joint tends to have an upward deflection also. And some of them are permanent due to progressive increase, and some of them are variable. in these movements. So you have to consider all of them when you look at the sources of joint movement before you take a call on it. Okay. The most important aspect for this joint is the every time you provide a joint, you're basically reducing the ride quality. So you have to minimize them. Then that's where the economy consider what's the price we need to pay for good ride quality versus what's the price we need to pay for installation and the quality and the nature of the joint. Okay, and as you can see, there will be always a vertical displacement and there will be a horizontal displacement, and basically the ride quality happens uh, if you recall how the way the rubberized wheel, it is a flat surface under the load, which is a contact. When that flat surface comes here, it flexes. It flexes in somewhat similar fashions. Just imagine that uh, from round to flat, if I just straighten it suddenly over a short interval of time, you see the air is pressed and the sound is produced. So it makes noise every time, even the tire when it goes over the gap, not because this joint is loose, just because the rubber of the tire from flat, it becomes rounded locally. That time it pushes the air underneath it, and that sudden increase at that high speed, and that noise is larger at higher speeds. Okay, and we are going in for higher and higher operational speeds on our bridge deck. So it has two parts to it. All joints introduce noise, all joints introduce a reduction in the ride quality. Okay, so what should be the requirement for a joint? They should respond to combination of movement, straight distance, change between the joint interface, the racking distortion, fine vibration, variation in skews, horizontal angle, all these traditional displacement, whatever causes differential displacement between the two slabs, that has to be considered. Okay. It has a second purpose, which is say that there is a gap. If you can't leave the gap here, because if you are in a rainy zone, then in that case, what will happen is the rainwater will go down and it will start providing deteriorating chemicals and entries to the pier cast bearing, etc. So that it starts affecting, apart from the fact that it start affecting the life of the other component below the deck also. So therefore, one of the purpose of the joint is to seal the entry to any foreign material from the deck itself, right? It should seal the entry of free water, absorb movement within itself without being extruded above or expelled from the joint, and withstand wear and tear impact from repetitive heavy traffic. These are all. And on road bridges, they have an additional thing that petroleum products and whether it should withstand their corrosive effect. So, what are the types of joints? The simplest of them is with an elastic material. This is what is called as in a traditional language as a compression seal. All you do is whatever is the gap, it is meant for, as you can see, it's a very small movement joint. So let us say if this gap is about 10 mm, you take maybe a 20 mm thick rubber, compress it, push it down. Okay, this is the simplest of the joint. Okay, and it can also, because of the friction between this and this, it can, and because of the flexibility of this, it can withstand a little bit of vertical displacement plus or minus 1 mm, and it can be used for more or less 90 degrees best. On other skews, it is not very good. Then you have something called asphaltic plug or modified bitumen joints. Basically, it's a material that straddles the two decks, and it is nothing but bitumen, but it has got little more what they call it plasticity in it, so that it stands movement in without going into fracture. So it can withstand a little larger set of movement, 10 mm. But I'm not sure. I have not seen any of them that take 10 mm vertical. I'll verify that whether it is 1 to 10 mm or much smaller than that, 1/10 of a millimeter. That's what probably it means. But it can be used on skews because it's a bitumen product, right? Then for larger movement, we can also have compression seal of larger. Now, if you look at it, this has got a compartmentalized elastomer. It is shaped, and this is also, if whatever is the gap, you produce a bigger one, squeeze it and keep it, and you have a bonding agent at the two faces so that it doesn't slip down. So this is a compression seal, compressed rubber beam they call it, because they can withstand much larger movement in the range of 25, and it can also withstand vertical movement of the order of about 3 millimeters. That's possible, and it is good for skew less than 30 degrees. Then the most common one that you see is what is called as a strip seal joint. Then it can withstand a movement of plus or minus 35 millimeter. The gap can be as much as 70 to 80 mm. It takes more vertical displacement of up to 10 mm it can stand, and there's a waterproofing layer in the form of a elastomeric sheet. It can be used for skews up to 45 degrees. There are only variations in the pattern of the anchors that you provide for these edge metallic beam. Then you have got reinforced rubber, which is what we call as uh, slab seal type. One other term you might notice in our code is uses the word slab seal type. So basically what it is elastomeric rubber, and it has got bolts that you can fix it, and it has got the elastic rubber has a reinforcement steel, just like we saw for the bearing. They have a reinforcement steel here, not continuous, but in broken. So the way when the expansion takes place is the rubber between them deforms and accommodates the movement. So this type of and the vertical load is transmitted by this rubber to this, and through this rubber through the same thing to this, so that there is no what they call it bump felt on it. So this is also good for about 70, 80 mm. These are more sophisticated slab seal type are available, which can take much larger movement. Let me see if I have got at the end of it. Yes, this is the reinforced rubber slab, same slab steel, the similar type, but with multiple corrosion in places in which the movement can take place. So this can take as much as 300 millimeters, 330 millimeters movement totally. And but generally this is not suitable for very large skew. Try to use them in this, and these are the holes through which you put the bolt to fix it to the deck on the two ends. So this is the what is called as a classical slab seal type. Then you have a single plate sliding joint, but not very common in bridges. In the horizontal for this single plate, that means basically you have a plate which is sliding from one end to the other end. So this joint is not very common for bridges, but in some places they do tend to use it. But for such large movement, you have either use the modular strip seal joint. So here you have the strip seal, what we saw as a single unit here. This single unit, you install multiple units of it here, and to accommodate larger movement. So each one is capable of accommodating about 70 to 80 millimeter movement, so that if you have large movements, you just increase the module. That is why it's called the modular joint. But it has a problem. It has a problem is that if it has got a mechanical component, which for a slow movements like temperature, creep and shrinkage, make sure that the gap between these modules are uniform. There is the mechanical arrangement there, and therefore it has to be periodically inspected and replaced. And in India, this modular expansion joints have become quite popular, because we also started to prescribe, especially for expressways and other things, that we need to what they call it, have a minimum continuous length of 100 meters, 120 meters, etc. Plus, if you notice that the bridge effective temperatures have been redefined in the code IRC 6, so that the range of temperatures which we have to design are much larger. So what is happening is those simple joints which we used to have no more acceptable in the code. So we are moving to a modular, and therefore while we might comply with the code, we are also bargaining and trying into getting into trouble with a higher maintenance cost. One example of a very large horizontal modular strip seal joint, for those who are in Calcutta, they can see it actually on the Hooghly Bridge. Hooghly Bridge has a fixed end and one abutment. and the 880 meters continuous length deck of the cable stayed bridge has all movement. I think, if I'm not mistaken, it has a 10 or 12 module expansion joint. It was recently replaced. It was recently replaced because that expansion joint, which they had fixed in 1992, had already failed because of the non-maintenance, and all the expansion gap were accommodated in one. So there was a very wide gap, and it was identified as early as 2003-4. Unfortunately, with our bureaucracy, the repair works actually commenced only in 2017, 18 or so. I'm not sure. Those who are from Calcutta, they can confirm that they've actually replaced and fixed that issue now. The last type, this is a very common and large movement in bridges, is a finger type, which I showed you. The finger can be inclined one like this or a straight one like that. The advantage of the inclined one is this is less noisy. This is more noisy. Noisy in the sense due to the air and the way the tire flexes on the gap. That's the only reason for noise, not that the level or profile is any bad. And this is suitable for very, very large movements, very large movement, but it has got another maintenance issue due to vibratory and the moving loads. The chances are the bolt anchors that at the top, they get periodically loosened. So they start coming out. So the maintenance regime must go back and retighten all of them at periodic interval to make sure that this joint works properly. So that's the last of it. In the next class, we will move on from joints onward to modeling, thereafter analysis, last design and retrofitting and ductile level. Maybe another 10 weeks or so, or 12 weeks maximum. We will go through the full introduction process. So any questions for the day? Day? Right? Or if you have a question, you can ask.
Hello, sir.
Yeah.
Sir, not on today's topic, but means the question was when we use elastomeric bearings,
Yes.
we don't use a response reduction factor, but whereas in what PTFE we use a response reduction factor over. So, why?
Why is
What
that?
was the reason? Yeah, what was the reason?
Okay, it is related to the fact that uh, response reduction factor is the reduction in the design force. Just hold on. Let me see if I can. Let me see if I can open out. Okay, I will. A part of my earthquake engineering training, I'll try to explain it to you. I think this slide will able to see my slide?
Yes.
Yeah, okay. So basically, what happens is, if you look at a structure from its load displacement characteristic. So one way to do it is I design the structure in such a fashion. Now, what are we doing in earthquake engineering? We're basically accommodating the relative displacement between the ground and the superstructure due to the inertial mass of the superstructure. Let's understand that's a basic phenomena, correct?
Yes, sir.
So the ground is moving, the superstructure due to its inertia wants to stay in its own place. That's the meaning of the word inertia, right? So when the ground moves, we have a various ways of accommodating the movement. So the one question is, we can accommodate the relative displacement. That means we know the displacement. We can accommodate it by having a linear force displacement rule. Then what happens is, to accommodate the same displacement, we'll come up with a larger design force, right? Now we have also said, basically, if you look at the force into displacement, the area of this triangle between them will give you the amount of energy that is dissipated in one such displacement cycle. We can do the other way around. We can say that, suppose I create a mechanism whereby accommodate a large displacement but for a smaller design force, thereby making the load displacement graph look something like this. Then the area between the same load displacement graph will be the same, equal to the energy of dissipated by a linear displacement. Now, to achieve this, basically to achieve the large displacement without increasing in the force, what do we need to do? We need to create places where the relative displacement can happen. So one such principle is the allowance of formation of plastic hinges. At the plastic hinges, you allow significant rotation to take place. The other option is that I introduce an isolation bearing between superstructure and substructure, wherein I allow the large displacement to take place between the superstructure and substructure through the displacement of the elastomeric bearing. Now, when we are doing, so response reduction factor more than one is used only when you allow the structure to have formation of plastic hinges. When you allow formation of plastic hinges, you reduce the design displacement design force by a factor called response reduction factor, which is always more than one. But if you allow the displacement to be taken by elastomeric bearings, then you cannot allow another place where you want to have a plastic hinge to form. Therefore, all the rest of the structure must be in completely elastic zone. So you cannot reduce the response further than what you get out of introduction of elastomeric bearing. Now, in both the cases, what happens is, in the by using elastomeric bearing between superstructure and substructure, how are we reducing the design forces? We are reducing the design forces by expanding the time period. How do I explain that? Okay, this is a good example. So let us say we have a choice. I use a superstructure with pot and PTFE bearing, and let us say I have put a pin bearing at the top. Then what happens is, my time period will be very small. It may be in the range of about 0.6, 0.7 second, natural period I'm talking about. If I introduce an elastomeric bearing, the structure becomes more flexible. My time period will go from that. So if I do that, my SA by G will be of the order of 2.5. And when I use an elastomeric bearing and therefore introduce the flexibility between the superstructure and substructure, my time period will increase. My time period will be anywhere from 1.5 seconds to 2.5 seconds. So in which case, what will happen? I will be designing for a SA by G value in the range of about 0.5. So you are reduced the seismic forces to 1/5 by introduction of the elastomeric bearing. So you can't further say I will reduce it further by employing another plastic hinge to form, and I'll say I'll reduce it by another 1/3. That is the reason why the code says that if you are using isolation bearing as elastomeric bearing, elastomeric bearing as isolation. Please remember, I can use elastomeric bearing as non-isolation also by introducing other restraint devices, which will make it equivalent to pot and PTF. It all depends upon your detailing. That is why no response reduction is applicable for structure designed with elastomeric bearing as isolation bearing. And response reduction factor is possible possible, I'm not saying always permissible, is possible for those which have got non-elastomeric bearing and you have a fixed free conditions between connection between the superstructure and substructure. When you do that, then in order to be able to design for smaller forces, you must make provision. You cannot arbitrarily use response reduction factor 3, etc. If you use higher response reduction factor, you can do it only if you have provided and detailed out a location where plastic hinge can form, where the relative displacement and between the superstructure and substructure can be accommodated. That is the reason for permitting response reduction factor for non-elastomeric bearing. But I want you to be careful. Just because you have provided elastomeric bearing does not mean you will have R equal to, I mean, you can, you need not. But suppose I provide elastomeric bearing only to take vertical load and rotation, but displacement I control through a restrainer, then it is as good as pot and PTFE bearing. Then though you are using elastomeric bearing, but it's only for vertical load, then you can have R equal to R greater than 1 also, but that requires you to allow formation of plastic hinge in some location. Have I addressed your question?
Yes, sir. Okay.
Anything else? If not, we'll call it a day and meet again next on 25th. Okay, right then. Good night, everybody.
Good night, sir.
Thank you, sir.